Okay. So if you are in the Zoom meeting, could you please confirm that you can hear my voice and see the screen shared with the introduction to data replication and the CAP theorem, please? And by the way, welcome to a new lecture of this course. Okay, so if you're in the Zoom meeting, can you hear me? Great. Thank you, Panitz. Okay. Great. Thank you so much, and all of you. Okay. So, so far, we have approached MongoDB. We have seen the basic queries, the find, the update. We actually haven't seen the delete. The delete is actually the same as a find, just that what is found has been deleted. And you will practice, you had practice in the last laboratory practice last week, and you will practice again this week, tomorrow, okay? But this week you also practice with a thing which is called replica set. So MongoDB is not just a database you install, you query, you do stuff. It's designed as in NoSQL style for horizontal scalability. So it's quite interesting to have a hands-on practice on having more than one MongoDB talking to each other and behaving like if they were a single database. Okay, so adding new MongoDB instances and looking at how this is transferring the data across the nodes, and if you kill one of the nodes, what happens, and all this stuff. So to have some hands-on on one of the features of the NoSQL, because so far you have seen the non-relational aspect, instance, no joins. We haven't seen any joins so far. You have seen the schema-free approach. Okay, so you have seen how to query a schema-free data set with the language of MongoDB, but the concepts are very much the same in other contexts. Okay, so an attribute can be missing, an attribute can be a list of items. So the list or array is a native type of NoSQL databases, and so on. Okay, all the stuff. Then we have seen the aggregation framework, which is I would say the counterpart of the extended SQL in NoSQL. Okay, we will also see something more regarding the MapReduce in the coming, probably next week. I don't know if this week, but next week, definitely by next week. Okay, so now we are focused on some features of non-relational databases. Specifically, I would say the no join and schema free. Okay, if you remember that slide with three issues, three features, okay? One was no join, another one was schema free, another one was horizontal scalability. Now we are addressing the horizontal scalability part of that topic, okay? So let's introduce this topic here. First, what's data replication? Okay, so the title is data replication. We are looking at data replication. That's not writing. Why? Okay, yeah, there is a very long lag. Data replication means I have the same data in different places. Very naive definition. When do you replicate data? Well, for instance, if you back up your photos from your mobile, you're data replicating, okay? If you do, you use an online email service, that's data replication, because if you use a client, probably the client downloads a portion of your email on your own computer. And so if you're offline, you can work with that. You have a copy of your emails on your client, okay? A copy of a portion of the emails, okay? So data replication happens many times in our life, okay, independently of NoSQL databases and data management. But here we specifically focus on, I would say, a professional grade data replication. The goal of the data replication here is to provide some features, we'll see in a minute which ones, in such a way that you are not responsible of managing that aspect. Okay, so when you check your email on your mobile, okay, and you have a client there, you're not aware of all the stuff which is going on in the background, okay, which is downloading, caching, checking new emails, and all that stuff. You just use the service, okay? So that's the idea with data replication in data management for NoSQL databases. I have a database. I don't want to lose data. I want database to be fast. I introduce data replication. And let's see what happens, because there are challenges. Okay, it's not as easy as it might seem. Okay, so first, same data means that I replicate my data. What is my data? Well, can be the whole database, can be some collections, can be some documents, can be a portion of it. So one question is, which data do I replicate? I do replicate everything, might be not. Second, in different places, where are the places? Because I might have, it happened to be, I used to back up my photos of my family on external hard disk, okay? Then the hard disk was on the top, on the edge of a table, and it fell down. And that was an old style hard disk with rotating disks. And so I've lost everything, okay, from the hard disk. And that was the only copy, okay? So if you have your data in the same data center and there is a fire or a flood, yeah, you might have 10 copies of the data, but they are all in the same data center, and you lose them all, okay? So it's better to copy something very far away, so that the probability of having two floods, two fires the same time in two far distant places, it's very low, okay? So of course you cannot defend yourself from anything, but you are reducing the probability of the failure, okay? That's the goal. However, if this information is very far from you, there is a trade-off, because of course I could have taken my hard disk far away from the table, but if the hard disk is far away, when I want to take a picture, recover a picture, it takes time. And that's the same in computer science. If you have a cluster, a node of the cluster far away, you pay the round trip time every time for every packet. Okay, round trip time, from network is the time required from a packet sent over the network to go to the destination and get back to you. Okay, that's round trip time, and it's capped at light speed. Okay, so you cannot just say, well, I have a very fast internet connection. If you're playing a game, okay, with Australia, it takes light speed of your cables or the satellite or anything to get there and get back to you. Okay, so that lag delay at the moment it's unfeasible to be surpassed. Okay, as far as we know so far. Okay, so that's a very hard limit. Okay, and so the farthest you put your nodes, the higher the cost in latency, in delay. Okay, and sometimes it's a problem. Okay, if you just do the backup of your pictures, I don't care if it takes, I don't know, 1 second, half a second to get to Australia in a hard disk in Australia. I don't care. Okay, but if you are playing a game, for instance, you need very low delay in your actions. Okay, and in some ways, in databases, you have some applications which have the same requirements. Okay, very low delay and in the execution. Okay. So same data, some data. In different places, can be a second hard disk in the same computer, can be another computer in the same building, can be another computer in another building in the same state, in the same country, can be another country, can be another continent, okay? That's the option. So, but what is the purpose of these? Well, we have two purposes. One purpose is redundancy, which means surviving the failure. Okay, the example of my pictures, or it's full of examples. Okay, so when you copy the same data in another place, to have a proper failure, you need to kill them both. Okay, so that's the reason why typically you have the so-called disaster recovery data center, which is far away from your business. Okay, so that if there is an earthquake or something like this, you have a second copy far away. And the probability of having two earthquakes, exactly the two places where you decided, of course, that's an option, but it's a trade-off between the investment in terms of costs and the probability of the failure. Okay. So redundancy means I can be available as a service, so I can provide my service even if I have a failure. Okay. There are some big data solutions like Hadoop, and I will talk about it a little, but you will study Hadoop later, your course of study here, which automatically make 3 copies of every data they have. So you send your file, the file is split into chunks, okay? And each chunk is copied 3 times in different computers and hard disks and racks of your data center, and possibly also in different data centers, okay, depending on your topology, okay? So 3 copies is default. Then you can change, you can say 2, you can say 4, you choose. But default is 3 copies, okay? Just to give you an idea, okay? That's one of the state of the art in big data management, okay? But that's not the only one, the only goal, okay? So surviving to a failure is nice, of course, because if you're a company, when you're a failure, you're not earning money. Your service is not working, okay? And you have issues with problems with customers, and you need to manage that problem and all the stuff, okay? That's nice. But the second point, luckily enough, I would say the failure, if you look at the failure at large in the sense of having a business which is stopped, it's not so common. Indeed, when there is an issue with you know the services we use the most, it's a news. They say, oh, it's a news. It's down for 1 hour. No, WhatsApp, Telegram, Facebook, or you choose the network, has been offline, or has been some kind of outages in some countries, in some places. Okay, and that's the news, because usually we're used to something which is working. Okay, 99% of the time. Okay. So the first point is important, but it's kind of defensive. The second point, better performance, instead is attacking the market, okay? So if you are a startup, you're launching a service, and your service is low, you tend to have no high success, okay? The performance means the velocity, how quick you can serve the request from your, I would say, application, okay? So in front of the application, you have the user is using your front-end application, being a mobile or a web application. And then in the backend, you have the data management system, whose purpose is to answer as quickly as possible to all the requests, okay? And here, the problem is that the more customers you have, the more you are having success. So it is a happy problem. However, the more requests you receive. And so the horizontal scalability pattern says, keep adding some nodes, okay? So you can keep answering requests, okay? But this is not so straightforward. So this works for a portion of the request. So next slide, we see the details of this. And so the point is, how can we improve our performance thanks to data replication, okay? So if it is clear how can we survive to a failure, how the data redundancy can help me in improving performance, okay? We have basically 2 approaches to answer this question. I would say 2 features to be analyzed, okay? One is, how do we connect the different nodes of the cluster? One option is, you see here, master-slave replication, okay? And the other feature is, how do we force the replication of the data? So do we force the replication to happen immediately? That is synchronous replication, or can we let the replication to happen later? Okay, and each of these choices have some pros and cons. Okay, so that's the core of the discussion. So let's see this schema, which helps us a little in identifying how this works. We are replicating data. Okay, so in some ways, someone is sending the data to be written to our database. Okay, this is our database. Okay, the database is the whole. From outside, our user doesn't want to, is not interested into looking into the details of our inner building topology of the nodes. Okay, so when you I don't know, check Gmail, you don't care about which server is serving your Gmail. You just want the email to work. Okay, and the same for WhatsApp or any service you use. Okay, so the user is asking the database, or actually through the mobile app is issuing a request, and the mobile app or the front end is then requesting to the database, to the backend, please do this, write these records, send this message, okay? So this insertion, this write operation, okay, is sent typically to a master, okay? A master is the main node in charge of receiving the write operations. So insert, update, and delete, okay? Then it happens in data replication. So after the write operation on the master, of course, the master can also answer the read operations because it contains all the data, okay? But that's not the goal of the master at the moment, okay? So in the master, you can either read or write or both, okay? But specifically on the master, you write, insert, update, and delete, okay? Then the other nodes called slaves will follow up. So they receive the updates from the master and they keep catching up with the new data arriving to the master. So basically the slaves are, let's say, kind of external hard disks, okay, from my laptop. I connect many external hard disks to my laptop and I keep copying all my data I'm working on my laptop as a copy to all the hard disks. Okay, so that's the idea. So I can add as many slaves as I want. Okay, so of course this helps in redundancy, in availability, because if there is a failure, okay, you kill one of the hard disk, external hard disk, I have the others. Okay, if I kill 2 or 3 of them, I have 4. Okay, I can survive 3 failures at the same time with this configuration. Okay, and so that's clear for redundancy. Okay. It's a little less clear for speed up, for performance. And here is the usage of the slaves for speeding up the service. Okay, imagine you are the Amazon catalog, okay, or an e-commerce catalog. Okay, the update operations of the catalog happens only when someone buys an item and you need to decrease the stock. Okay, or when the owner of the catalog or the seller is changing the data of the product, like the price or the description, or adding an offer, special offer. But this is much, much less frequent than the amount of times customers read the catalog. Okay, if this is a successful e-commerce, okay, if nobody goes to see the e-commerce, that's useless. But if you are having success in this e-commerce, what happens is that probably you have 10, 20, 100 times more read operations than write operations. Okay? So you send the write operation to the master and you send the read operations to the slaves. So that if I'm having success and much more people is browsing my catalog for buying items on my e-commerce, as soon as I see that my slaves are not enough, because imagine that each slave can serve the requests of, I don't know, 10,000 customers, okay? So each of these is 10,000 customers, okay? If I'm having success, probably in a few days or months or weeks or hours, depending on how much success you're having, these slaves are not enough anymore, okay? Because there are so many people, so many customers browsing the catalog and looking what to buy, that you cannot sustain such a high traffic, okay? So the solution in horizontal scalability is keep adding slaves, okay? You keep adding slaves, the slaves copy the data from the master, so the first copy will take a little longer, of course, because you must copy everything. Then when you catch up, you only need to update the changes, so it's very tiny operation because it's only the delta, the difference, okay, the change set, okay. And from that moment on, you can use that slave as a new portion of your service, okay, which is serving again 10,000 customers more, okay. So that's the idea, and virtually that's virtually scalable without bounds, okay. So you can keep adding slaves as much as you can buy them. And besides that, you have no real limitation, okay? You need, of course, in the middle to have a kind of dispatching system like a Kafka queue system, but we are not interested in what happens in the middle here. Okay, you will see that MongoDB will allow you to make such a system and automatically takes care of dispatching the updates. Okay, without anything in the middle. But in very complex architectures, you might have there in the middle a dispatching system. But we're not focusing on that aspect now. Now, the point is, with this solution, I can use horizontal scaling for speeding up my system virtually without bounds. Okay? Keep adding slaves. Okay. So what's the problem of this solution here? One problem is the master is only one. So if the master fails, I can still provide the catalog of my e-commerce, but nobody can buy, which means I'm not earning any money. Okay, so that's a problem. Okay. In MongoDB, what happens is that when the master fails, one of the slaves is elected as a new master. Okay, since the hypothesis is that the slaves have the same data as the master. So any of the slaves, then any of the slaves depends, because you might have the slaves in different data centers. You might have the slaves which are not as powerful as the master. Okay, but given some differences in architecture and hardware, from a data point of view, it can be elected to become a master because it contains the same data. Okay. However, that is not always true. Why? Let's see the synchronous versus asynchronous replication. What I've just said, that every slave can become a master, is true only if the slave contains the same data as the master. But for this to happen, we must be very careful to the process of the update. Okay, so I am the customer, the end user. Okay, it can be the mobile app, the front end. Okay, I'm on the front end side. Okay, I'm asking to update something, insert an item, or buy an item. So decrease the stock by one, anything, but a change. I need to change the data. Okay, so I issue this command here. So that's point one. Okay, the master receives the update, and of course it can save the data, save the new value on its own hard disk, and that's okay. However, to be sure that in case of a failure of the master, everybody has the same data, it must, number two, update all the slaves. Okay? When all the slaves say, I've updated, I acknowledge I received and I saved the new information, the same as you, my master, okay? It replies, okay, can reply at that point, so waiting all answers from, that's number three. And in the end, after all the slaves have replied, yes, I'm updated, the master can reply to the end user, to the front end, okay, saying, I've done it. So you might imagine this takes a long time, because if all the slaves are together with the master, very near to the master, they just wait the command from the master, probably it takes a small amount of time, okay? However, being near to the master is the anti-pattern of the redundancy, because if I'm near to the master, in case of fire, flooding, or any issue, all of them will die. So what you tend to do is to take the slaves away from the master, because the goal is redundancy, surviving to the failure. Okay, and so you move the slaves away, which means a long round trip time, which means you wait for each update. You wait every time a round trip time. So imagine that the master can sustain, I don't know, 10,000 requests per second alone. If you wait for someone which is very far from you, every request is not only so fast, a millisecond, is 100 milliseconds, which means you cannot sustain the same set of updates. Okay, so you become slow, which is something you don't like, because we did this solution, we designed this solution also for increasing performance. Okay, so what happens is that actually you have a read scalability. Okay, you have a read scalability because these, it's written here, read scalability. Okay, and you see only read scalability. Because in writing, you still have a bottleneck, only one master, and a single point of failure, only one master. Okay? So if you want to trade off redundancy, which means availability, you lose performance. Because in this situation, I'm absolutely sure I will never lose anything. The only way to make me lose the data is to kill all the slaves besides the master. Okay? But if you tell me, please, I don't know, write this transaction, okay, purchase this item, I'm sure that when I get back to you saying I've done it not only myself as a master, but all my slaves have also copied that information to their own hard disk. And so in case of a failure, I'm kind of happy to die because I have my slaves ready to carry on the situation without any damage, without any loss in information. Okay, so that's the point. However, this is a performance killer. Okay, this is kind of unacceptable. This, I would say, never used in any situation. Okay, you might have very slow amount of slaves, so can be kind of acceptable. Otherwise, you tend to have other solutions. On the other side, the opposite behavior is that when you get the update here, okay, so you have the user which asks for an update to the master, okay, the master answers immediately, that's okay, I've done it, okay, immediately. So I can go as fast as the master can, so that's the fastest option. However, the slaves will catch up later. How much later? It depends. Can be milliseconds, can be tens of milliseconds, can be hundreds of milliseconds, can be seconds, can be minutes. Okay? It depends. Okay? So if there is a failure in the master, you might have lost something. Okay? However, this is the highest performing solution because you don't wait for nobody. You don't wait for any slave to answer. Okay? So between these two extreme options in real life, what happens? One of the very common options of MongoDB in this situation is to wait for the so-called quorum. So you wait for at least half of the slaves plus one to acknowledge the update. In that way, when you need to elect a new master, in case of a failure of the master, you have quite a lot, depends on how large is the number of slaves, of course. If you only have 2 slaves, that's not so a large number. But anyway, you have at least 1 slave, but generally much more, able to be elected as master because it has a copy which is actually updated as the master. Okay? Instead, you don't wait for the faraway slaves because all the slaves in the slides are on a row, but actually one is here in the same data center, okay, the first one. Then another one is in Italy, okay? And this is in Australia. The last one is in Australia, okay? And this is in the same data center, so it's kind of, okay, there is a lag here. Let's see, okay? And this is Italy, okay? So they are in different places, so they don't have the same performance looking from my point of view of the master, okay? That's independent from the hardware of the slave. It's the time required to go to Australia, write the packet in the hard disk, the update on the hard disk, and get back to me. Okay? So you have different delays by the slaves. If you wait for only the fastest ones, with the quorum approach, for instance, so which is half plus 1, half of the slaves plus 1, you improve a lot the performance because you are discarding the slowest ones, okay? While keeping redundancy because most of them have the information. Okay, so this is very common solution in big data and in scalability. Okay, and this is possible also with MongoDB, by the way. Okay, so please.
Let's say the past copy the same data and then slaves update themselves.
So the question is, yeah. So yeah, the solution your colleague is proposing is the following. I have an option like this, okay. And then I have something like this. Okay, there is a lag, but it comes. Okay, that is the master. This is slave 1, slave 2, slave 3, and slave 4. So the idea is the following. I have a master. I have slave 1 and slave 2 reading data directly from the master. And then I have slave 3 and slave 4 reading data from slave 1, because slave 1 is very near to the master. This is a possible solution. I haven't seen that in MongoDB, as far as I know. Might be, but I don't know. This is actually used when you need to dispatch the updates of Windows. You have an option which is get update not from the server of Microsoft, but from a local PC running Windows locally. Okay, so this is a kind of distribution similar to the distribution network like peer-to-peer. Okay, so if you find a peer which is near to you and has the same data, and data must be signed and certified, and you must trust that, and all the stuff, then you can do that. But as far as I know, in databases, that would be interesting to see if there is some products doing that. That's managed at application level in the case of Windows updates, as far as I know. Okay. Because in databases, you are very low in hierarchy in the data. You see raw data. For instance, you cannot sign the data, so you must trust. You would probably configure that manually in your configuration. So that would be possible probably. Okay, please. Yeah. Yeah. That's interesting. Is saying the following. Imagine that update of the master. This is the case he was mentioning. The update of the master is malicious. Okay, so I'm deleting a picture I didn't want to delete to make it less malicious, but anyway, it's a damage. If I propagate this to all my backups on the hard disk, then I've lost the picture forever. Okay, so that's a different issue because here the point is our context is I'm serving requests from a front end who is in charge of guaranteeing that they are legitimate. Okay, so if you ask me, please update this information, I will do that because that is the right thing to do. Okay, what happens to avoid that option is you have an historical versioning of your data. Okay, so you do checkpoints every day, every night, every hour, depending on how much you can invest of your data, and you don't change that anymore. You keep for 30 days, 1 month. Yeah, 1 month is 30 days, 2 months, 3 months, 1 year, depends on how much money you have to invest on that and how important is your information. Some, I would say some applications who really need that kind of integrity, they work by append only. So you cannot change anything apart from appending new values. So you keep the whole history. You can always revert like Git. If you use Git versioning, that's the point. You can do whatever you want and you can always get back because everything is saved. It's not you deleted an item, it's deleted forever. You delete an item, you mark that as deleted. Okay, when you do the checkout later, that's not check it out. But if you go back in the revision number, you can still check it out. So that's an approach used for, I don't know, transactional systems in finance. And also for sensor data, for instance, you cannot delete the sensor information. You say that in sensor information is anomalous, is unacceptable, but you still keep it. Okay, because it's interesting to know that happened, that an anomalous sensor information has been sent. Okay, so that's the case. How you solve that basically? You propagate the malicious information to all of them, but the malicious information is just an append to that. Okay, and so you can still revert that information, and if you query any of the slaves, you can have the same history of facts, of events, including the malicious information. Okay. Yeah. 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 I use the backup as an example that everybody can have experience of, to motivate the need of data replication. One of the needs, actually, redundancy. Okay, redundancy. In general, you also have other aspects to be addressed in general. So the topic will be larger to be explored. We focus on the key points. Okay, the key points are the points you see in any you can avoid to see at least these. An example of your use case is ransomware. Okay, if you have a live backup, you also back up the ransomware version of your data, and so you lost it. Okay, that's there. Yeah, great. No, okay. Commit is a terminology which is here, ready to commit. This commit. Okay. To commit in databases means to save the transaction as done. And so that is immutable. So it's like signing a contract. You sign the contract, you've done. Okay. So committing a transaction is when you write the result of the transaction in database and you acknowledge your client that you have done it, and it will be like that forever. Well, until the next update, of course, but it's durable. It contains the ACID properties, which we will see later in the slide deck. Atomic, in this case, we don't care about the atomic, so I've done it all or none. Consistence, which consistent means that it respects the rules of the database. So primary keys, there are no violations of primary keys, no type violation, no domain violation, so on. Isolated means that when you did that transaction, it's like if it were alone. Okay, actually, it has been done in parallel with other thousands of transactions, but the transaction itself seemed to be alone. Okay, and durable stands for the fact that when you've done that, it stays forever. It's not volatile. It's not in RAM. Okay, it's written to a durable memory, or anyway, the system, even if it's a RAM, has some ways in which guarantees that the data stays there kind of forever or until the next update. Okay, that's committing. No, malicious means that it's like deleting your picture. Okay, if I'm managing my backup of my pictures, I delete the picture by error. Okay, because just my fault. Okay, I didn't want to do that, but I did that. That's malicious, not intentionally. Okay, then the deletion happens on the master. That propagates the deletion to all the slaves, and in a few seconds, my picture is lost everywhere. That's the point. Okay, but that problem is addressed by solutions like Git versioning, like append only. So it's addressed in a different architecture point, not here. Okay, here the point is I propagate what happens on the master, and that's my job, so that every slave sees the same data as the master. If it is correct, it is correct. If this is wrong, it is wrong. But the goal of our service now, our design, is to provide, to guarantee that all the customers connecting to a slave see the same catalog as the master. Then if a person in the master changed the price of an item and inserted a wrong price, that's another problem. Okay, we are the database. We don't look at semantics. If the price is wrong, there was the front end whose purpose was to say, hey, this is anomalous. I haven't seen such a value in a long time. Are you sure? Something like this. Okay. Great. Okay. Other questions? I forgot that you had some questions in the Zoom chat and also in the Piazza. I wanted to answer those questions. I forgot to at the beginning of the lecture. After the break, I will answer those questions for you. Okay. Remember me, because I wanted to address them all. Okay. Great. So that's synchronous, asynchronous replication. Yeah, so we've seen that. And in the middle, we have the quorum approach, also used by MongoDB, okay? Which means I don't wait them all. It's like when you go out on Saturday night, you wait for some friends, then that friend which is arriving too late, you don't wait for him, okay? You just go and he will arrive later. That's the idea. You cannot spend all the night long waiting for someone. So here, if you have the slave in Australia, waiting for him or for it, it's very expensive in terms of wasted time, okay? And not really necessary for redundancy. That's the idea, okay? So that's a trade-off. So given that, now we can focus on what are distributed databases, okay? So in distributed databases, we have what? We have one database consisting of many nodes, but from outside, I would like the database to behave as if it were a single unit. Okay, so the behavior of a database on a single PC, a server under my desk, should be the same as the behavior of a database with many nodes across the globe. Okay, that is our goal, I would say our desire. Okay, then it's not like that. Why? Because the node under the desk, it's like me organizing a pizza with myself. It's very easy. I decide when I want to go, I go, and that's it. If I have a distributed database, it's like organizing the pizza all together, and you want all of you to be present at the same time in the same place. Okay? Quite difficult, I would say. Quite difficult. Okay? And that's the point. So when you want to make a distributed system with many different autonomous entities, because there are different PCs with different power plugs, with different hard disks, with different operating systems, scattered across the globe, that's the most general approach, to behave as a single database, we face the same problem as the pizza of the course. Okay, so let's see these problems. Okay, there are three features that every distributed system has. Okay, these three features are: first, consistency. So consistency means that I'm here, okay, and you are there. Okay, so we're different customers. I connect here, you connect there. Okay, this is the database. So from outside, the customer A and the customer B, if they ask for, I don't know, booking a room for a holiday in Christmas time, the same room, the same hotel, the same period, okay? If it is free for customer A, it must be free also for customer B. If it is booked for customer A, it must be booked or for customer B. Okay, that's, I would say, an expected behavior. Okay, so for every query I launch at my database, the answer must be the same from any point I queried the database, which means that every node must have the same data. That's the only way in which I can guarantee this behavior. Okay, this is called consistency. All the databases, I would say all the nodes of the database, provide the same data to the application, which means replying the same way to any query. Okay, that's consistency. Then we have availability. Availability means, to make it short, means are you earning money from your service? That's availability. So is your service functioning, operating, and making money out of it? Okay. Remember that if you take this definition, which is more managerial than computer oriented, you actually get the right answer. Because if you have a system like this, let's take this system here, okay, with a failing master, okay, if the master has failed, okay, you can still read your data. So you can still provide the catalog of your e-commerce to the customers because they keep querying the slaves, but they cannot buy. And so you are not earning money, okay? And this is not available indeed. Even if the catalog can be browsed, okay? You can access the catalog, you can read it. That is not availability because you are not allowed to do, I would say, the most important thing, which is buying. Okay, so you build up the catalog with the purpose of allowing customers to buy something because you earn money when someone buys something, not when just browse the catalog. Okay, so that's not available just because the catalog is available for reading. That's unavailable as a service because you cannot do the core of the service, which is buying stuff. Okay, so that's why I give you this definition of availability, sorry, which is more from a managing point of view than scientific point of view. But this drives you to the core of the question. Are you available? So are you earning money from your service? Is it fully functioning, fully operational? That's availability, okay? And of course, if you are in distributed setting, you typically have a large number of nodes. And so the failure is happening quite often, okay? You know, typical question, I think I already told you. If you look at one person, so it's me, okay? When I'm ill, low probability, luckily, okay? When one of us is ill, it might happen once a week. If you look at the whole Polytechnic or the whole city of Turin, at every hour, there is at least one person who is sick. Okay, so if you look at that from the hard disk point of view, if you have one hard disk, probably it works for years without a failure. If you have hundreds of hard disks, some failures happen every month. If you have thousands of hard disks, every day there is a failure. Okay, so here, regarding the failure, the point is your distributed system, which is probably built by many nodes, hard disks, and parts, okay, able to survive a failure, okay? And that is the question we addressed a little before about this. So if the failure addresses the master, for instance, you have a problem. If the failure addresses a slave, you have no problems with this architecture, okay, with this architecture, okay? So that's availability, okay? So of course, we would like to be consistent, clear, that's clear. We would like to be available, even more clear, because we are earning money. We also want the partition tolerance, okay? So the idea is the following. In a setting like this, it might happen that sometimes the network goes down. Why? Because it's a distributed system. Distributed system means that to let the system work, you need to talk to the other nodes, okay? So if we need to organize the pizza of the course, we need to call all the students enrolled, okay? If someone doesn't reply, we cannot have the pizza because the purpose is to be all the students enrolled in the course present at the pizza. But to reach that goal, we need to at least speak with the students, but if they don't answer to the call, you cannot do anything. That's the network partition, okay? That node, that student is not answering. I cannot reach him or her, okay? So here, if I cut the connectivity like this, okay, A and B are connected to different nodes. They don't talk to each other, okay? That's partition tolerance. If you are partition tolerant, then you survive this cut and you can still work, okay? You can still operate. If you are not partition tolerant, then means that you have no such a feature, okay, like the pizza of the class. Okay, so these are the three core features, characteristics that you find in any distributed system, and specifically in distributed databases. Okay, what's the theorem? Very simple theorem. You have the history here. It was initially a conjecture, then it was proved as a theorem. You see, it's quite old as a theorem. Now we are also beyond the theorem. I will tell you something about it during this story of this slide deck. The theorem is very simple. You cannot have all the three at the same time. Okay, so out of these, you choose two of these, and you can have two at the same time, but you cannot have all the three at the same time. Okay, why is it so? So I will not prove the theorem with maths. I will prove it by narrative, by intuition, and simply work like this. First, I cut the network like this. This is a network partition. Okay, so network partition means the theorem name is CAP. Why CAP? Because CAP are the initials of consistency, availability, and partition tolerance. Okay, so that's the name CAP theorem. Okay, from CAP. Okay, so I want to keep the P. Okay, let's say I keep the P. Now the game is, can I have both C and A? Let's see what happens. If you want to keep the P, this is the P, the network partition. I cut the lines, and I suppose I want to demonstrate I can be both available and consistent at the same time. Okay, let's see if I can. First, I have customer X and Y now because I need the letters for CAP. Okay, so I have C, A, and P here. So the P is lagging. No, what's wrong here? Okay, the P is taken. I've done it, P. Now, which one you want, C or A? You choose. We do both. A. Okay, great. So want A. I want to be available. Okay, to be available means that X and Y, the two customers, can book the room, can buy the item on e-commerce, can do some write operations on my database. Let's imagine it's booking a room, just for the purpose of the example. Okay, so both X and Y want to book the room. They want to book the same room in the same period for the Christmas holidays. Okay, by chance, might happen. Okay, so the customer Y will book on this node the room to his or her or his name. Okay, for that period, that room in that hotel, and so on. X will do the same, but the name is X name. Okay, so what happens? That in this node where X is talking to, that room for that period is booked to X. Instead, in the other node in South America, okay, the customer Y has booked the same room, the same place, same period for him or her. Okay, so are we consistent? We are not consistent, because if you query the database from the, let's say, American side, you will get the room is for customer Y. If you query from the Europe side, okay, Europe and Africa side, then the answer is that room is for customer X. So that's not consistent, because consistency means all the databases, all the nodes provide the same data to the application. That's not true. We provide different data. So we were available, yes. We earned the money twice for the same room. Very good, okay? But we're not consistent, okay? And we cannot be in any way, because to be consistent, I should send the information from Y to X. They should talk to each other, okay? If you take the same example for the pizza, it's like, no, we decide the pizza here, and someone else, which is not here, but it's a student of this course, so should come to the pizza, is organizing for another moment. Okay, we have two pizzas, not one pizza. So we diverge. That's not consistent. Okay? Let's change it. Okay, so now I decide I want to keep the C. Okay, we'll lag. Okay, see? Okay, let's see what happens. I want to be consistent. So to be consistent, I must guarantee that all the nodes see the same data. What's the only thing I can do? If I change nothing, they will be consistent. But any change I will do from any side will generate an inconsistency. So the only thing I can do is you can read the catalog, you can read the available rooms, but I cannot accept any booking. Because if I book a room, I'm on the American side, I cannot propagate the change to the Europe side, so they will diverge, so it will not be consistent, and this vice versa. Okay, so the only thing I can do to be consistent, where consistency is the current situation, as soon as the network partition is generated, just right before the network partition, the database was consistent. Okay, when the network partition happened, I had to stop updating data to remain consistent. So I'm not available because I just provide the catalog, the reading of the data, but I don't accept any booking. I'm not earning any money. Okay? So as you see, if you fix the P, you can either have the C or the A, but both is impossible. Okay? Of course, you can also say, I don't take the P, I take only the C and A. Okay? The problem with that is a very special case, because the case in which you have no network partition and you are both consistent and available is when you have a single node. In a single node, PC, desk PC or a notebook, you have no network partition because there is no network. It's itself alone. So that case is actually, I would say, a corner case. Okay, because in the case when you have no distributed system. Indeed, in a distributed system, you have the network, and the network can have a partition. Partition, which means the internet is down for a few minutes, for a few hours, or if you have experience with the mobile in the mountains, you go with your mobile in the mountains, and for some periods, you have no connection. Okay, that's a network partition. Okay, and indeed, if you write something on your mobile and it's not sent, your database is diverging from the database other people read in a group chat, for instance. Okay, that's the example. Okay, so that is what happens with the CAP theorem. What I just told you is, yeah, that's the narrative the was born on. Okay, yeah, this example describes what I've just told you with my drawing. Okay, and an example. You also have some examples here of different databases taking CNA, AMP, and CMP. Okay, why I tell you so? Because first finish these slides. CA without P, local consistency. This is the case in which multiple dependent systems do not need to interact. Example. Okay, that's the example of a single node. Okay, I have the Polytechnic di Torino students. The students are separated into the Turing campus, and I think there is a MongoDB campus or something in Varese. Anyway, we have the Polytechnic di Torino students divided into 3 different campuses. Okay, every campus has its own server serving only its own students. Okay, I can be in this situation because I can disconnect from the others and I have no problems of consistency. Why? Because I divided the authority to operate by geographical location. So the node in Corso Duca, in main headquarters, is working only on the students in the headquarters. The node in Architettura in Castello del Valentino is working only on those students there. The node in MongoDB is working only on the students in MongoDB. That's it. That's actually not a distributed database. That's data partitioning system, because there is no operation apart from transferring a student from one node to another. So I change degree, so I want to move from Valentino to headquarter or MongoDB. Apart from that operation, the normal enrolling, if you enroll here, I don't need to ask to anybody else of my nodes if I cannot do that. Okay, so that would work if, let's get back here in our example, if I say all the rooms in South America are managed by the node in South America. All the rooms of hotels in Europe are managed by the node in Europe. Okay, so I divide the data ex ante, a priori. Then what actually happens is that the network partition, when happens, means that X cannot book a room in South America and Y cannot book a room in Europe. Okay, so it changes everything. So if you remove the P as a property, you're actually talking about independent autonomous systems and not a distributed database as a whole. Okay, please. Yeah. So the point of your colleague is this division into different autonomous entities exposes your solution to more, it's less secure from a standpoint because everyone is exposed. Indeed, this solution where you have CA and not P, it's something which is not of interest. Because the situation where you're not developing a distributed database, you're developing independent databases which are not redundant, which are not connected. You just provide a similar service, but it's like having, I don't know, a different booking systems. So the booking system from South America, it's one, it's there. The booking system from Europe, it's one, it's there. You have no data replication among the nodes. You have data division among the nodes. So that case is not of interest, which is this one, is not of interest for us because not a distributed database. Please? Yeah, you can have it. Yeah. 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 Yeah, that happens. I will repeat that because that's interesting. In MongoDB, it's called sharding plus replica set. You can have the following. Let's draw it there. I think it's drawing it's better for your understanding. Besides the lag of this PC. Okay. The idea is the following. I have, well, we can have it like in Europe. In Europe, you see, in Europe, you have two nodes here. Let's see if the lag goes away. No. Okay. You have two nodes here. Okay. So imagine these two nodes are in charge of European. Okay. And then you have two nodes here in charge of South America. So you might have data replication within Europe and within South America and within North America as well, okay, but different regions. So you have redundancy locally, but you don't have the redundancy globally. Okay, that's an approach which is kind of used. The division is called sharding in MongoDB, and the local replication is called replica set. So you can do that actually. The problem is that if you zoom into, okay, into Europe, and you have these two nodes, you can repeat the same reasoning we did by a partitioning in the middle of the two. So it's just a matter of zooming. Okay, so it's a general solution which is adopted, so it's clever in some sense. But we are talking about what happens when you have a group of nodes sharing the same data as we discussed before. So when we are here, the purpose of these is that all the nodes have the same data. If you divide these having Europe data, American data, it's not a distributed database. There are two databases, one for Europe and one for America. So the new problem is, okay, let's zoom in Europe. Imagine there is a partition in Europe. You have the same reasoning, so CAP, the same, okay? Fine, okay, thanks for the question, that's interesting. So CA without P is actually a non-issue. So it's talking about a world where you have non-distributed databases. You have different autonomous systems working on their own, on separate data. There is no data replication here, okay? Instead, these two are the ones we discussed, okay? So CP without A is called transaction locking. I will show you what transaction locking is and how it's addressed in relational databases, okay? Because relational databases use this approach historically, okay? Nowadays, you know, this hybridization process, it's not like that anymore. But historically, relational databases relied on transaction locking. So if the coordination of the course pizza cannot reach all the students, no pizza for nobody, okay? And that's preserving, I would say, the possibility of being consistent. So you will never find the wrong data in your database. However, the risk is you don't earn money. Okay, at every failure in your network, you stop earning money. Okay, which sometimes is not acceptable. Please. Yeah, that's a clever possibility. He's saying the following. Let's get back here. Let's say that America is primary in our strategic decisions, okay, for any reason, okay? So this one. I have a network partition like this. What happens is that, okay, what happens is that I allow the availability on the American side, and I stop the availability on the Europe side, okay? Actually, this is perfectly compatible with the CAP theorem because you still have A and P and not consistency, because since America is updating data and Europe is not, if you ask from Europe, is this room free? They say yes, it is not free, actually, because someone in America booked that. So it's perfectly fitting the CAP theorem. You lose the C, you have A and P. And your option is a strategic choice, okay? But in that case, my option would be, since you let the American people book the room, why don't let also European people book the room? I earn double the money. Yeah, and here it comes. Thank you for this, because that is the cornerstone of the solution. Let's go to that point. That's very interesting. Too much engineers here. Okay, that is the AP option. Okay, so this is the historical relational database word. Okay, with two-phase commit. I will describe you the two-phase commit because I expect not all of you know the two-phase commit. The point is, in this case, no incoherence. So as you said, I don't want two customers complaining that I've made a mistake and I gave them the same room. Okay, that's a shame. Never happens because I'm very perfect. Okay. That is instead the option of NoSQL, okay? Introduced by NoSQL. Nowadays, you have very different nuances, but introduced by NoSQL. The idea is kind of optimistic lock. So I say the probability that two customers book the same room in the same period during the network partition, which is probably a few minutes, a few hours, it depends. It's something whose purpose is not to stay there. Okay, so when I cut the network like this, I'm not saying this is cut forever. Otherwise, it doesn't make any sense. Okay, it's a cut because there is a network congestion. There was a cut in the wires. There is unfortunately some wars or something bad. Okay, it's something bad anyway, which you expect to be transient. And transient can be seconds, minutes, hours. So what's the probability that in seconds, minutes, hours, two customers book the same room, the same time, the same hotel? Low. Then how much low? That depends on your strategic decisions, your marketing views, your values in your company, and all this stuff. But it's low anyway. First. Second, if that happens, What's the problem? The problem is that I need to contact the customer and do a post-sales management, okay? But the point is, if I stop booking at all, like in the let's say CP option, if I stop booking at all, for the whole duration of the network partition, I make no money, zero, okay? I have no post-sales cost because no issues will happen. If I use let the American and European book at the same time, okay, I will earn a lot of money. Depends on how successful I am, because if you are not successful, probably there is no conflict because nobody's booking. If you are successful, it means you earn a lot of money. So the conflict is more probable, but the money you get is much more not probable, sure, okay? So the idea is you tend to have, if you have a successful business, so much money in addition that managing the few cases of post-sales costs a tiny fraction of the money you got. And so you probably want to gift a suite in the best hotel of the world to a customer, no problem. That's a tiny portion of the additional money I got from keeping the system available in both sides, okay, in both sides. So that's the idea, which is, I know it's very managerial, less, from an engineering point of view, it's kind of hard to digest. But the point is that it's a cost-effective function, okay? You put on the same balance the cost of the penalty, the conflict, and the income from making the system available. And you see that generally, that depends on your business, okay? Generally, because if this is kind of life-saving, okay? You're doing something which depends on the life of the person, you cannot do that. But booking a room, you know, typically you book in advance, you have time to manage, you have options, so it's something which is acceptable to have a conflict on, okay? That's in general. Or if you're buying the last item on Amazon, okay? I'm buying the last item in America and the last item in Europe, and they cannot synchronize in time. I issue an offer, I say, well, I'm sorry, I made a mistake. Let's take, twice the amount in free gift. You're kind of happy. You're kind of happy sometimes, okay? So the trick is at application level, you transform this conflict into a marketing intervention. Because if you get the conflict like this and you get the suite in exchange, probably you tell your friends, this is a good company, they offer me a suite, okay? So that's outside of our technical aspect. But the point is, let's understand when a problem is actually a problem and how much the problem costs. Because sometimes we create the problem, okay? The problem is less than what we think, okay? So that's the idea. And this is what basically emerged with NoSQL, okay? So NoSQL adopted this strategy due to the period of time they were born on, when there was a boom in digital services, when the core was to, I would say, take off as a startup, okay? So if you're earning a lot of money from this system, to make the system not available is very hard. You want to privilege the availability, which means making money, then the consistency, okay? And this is a trade-off. Of course, someone must be kind of responsible evaluating the cost, the pros and cons, because then you must have a good post-sale team to manage the problem, to detect the problem in time, and we'll see a little more about that, because the database can help us in detecting the problem. As soon as the network partition goes away, it can reconcile the data and at least detect the problem. Then deciding to which customer the room has been booked is not probably the database task, okay? Should be done by human or someone else. But at least detecting the conflict is something the database can do automatically, okay? And we'll see that later, okay? So that's the CAT theorem. This is interesting. This is Werner Vogels, at that time was the CTO of Amazon. Here the point is the following. when you need to reconcile the database or you need to organize kind of the pizza of the course, it's a bottleneck if you have an algorithm requiring you to talk to each other. Okay, so it says that not actually for the pizza of the class, but for the fact that if you wait until the network partition is gone away, because your algorithms, it's like the two-phase commit in relational databases, which expects to talk to each other and waits for the answers, you never converge. Okay, if you ever organized events for a large number of people, you don't wait for all of the participants to say, yes, I'm available, no, I don't like, because you already know you never reach the convergence for all of them. Okay, so you go for a probable date, a probable moment, you just query probably some of them, and then you say it's like that. If you can join, you're welcome. Otherwise, we cannot just wait for all of us to answer. Okay, that's the style of the NoSQL towards the distributed decision. Okay. Beyond CAP, because CAP is not the end of the story. What happens? First, we have seen availability. Are there any system who is 100% available? Not really. Even if you look at the SLA, I don't know if you know about SLA. SLA is Service Level Agreement, okay, SLA, Service Level Agreement. It's the agreement on the level of the services you get from a digital provider. For instance, you buy Google Cloud. In Google Cloud, you have an SLA. You buy AWS, you buy Azure, you have an SLA. SLA says, I'm available 99.99% of the times. Okay? Okay. That's the SLA. So it means that sometimes it's not available. If you multiply that percentage for the hours in a year, I think it comes something like 4 hours or something like this. You can try, okay? But it's something large. You say 99.92%, it's always available. Not always. 4 hours a year. If those 4 hours are exactly when you have the exam, you have a problem, for instance, okay? The problem is you don't know when the 4 hours happen. It might be when you don't need it. It might be exactly when you need to do your most important exam in your life, and that's offline. Okay, so this is to tell you that even the best services in our world, Google, Amazon, Microsoft, you choose what, sometimes have a failure. Okay, a failure due to maintenance, human errors, anything. Okay, anything. Okay, so in the end, there is nothing which is 100% available. Okay, so availability actually is not always present by design. Not by design, because it's not designed, but by experience. It's a fact of life. Okay, we are imperfect. Okay, first. Second, consistency. We are seeing consistency in this example. Okay, in this example, that's the asynchronous replication, okay, with Australia, Italy, and so on. But is the Australian slave node consistent? It's not consistent because the Australian copy is lagging behind by 1 second, more or less. So if I ask to the Australian database, the catalog, the booking of the rooms, in that very milliseconds between the write in the master and update on the Australian slave, I will get the wrong value, old value. So again, consistency is not that I have consistency, I don't have consistency. Consistency is something you reach eventually. Eventually doesn't mean in Italiano eventualmente, that's a false friend, means in the end, after a while. Okay, so I introduced this adverb because it's used later. So eventually consistent means I'm becoming consistent after a while, eventually, in the end, okay? And after a while means 1 second, 2 seconds, 100 milliseconds. even the slaves very near to the master, they become consistent 1 millisecond later, 2 milliseconds later. Okay, so if you do a ping, which traces the round trip time in Italy from Turin to Milan, you have 10 milliseconds. I did the speed test last time from my home. I had 30 milliseconds round trip time. Okay, 30. So if I ask something in that 30 milliseconds, even the nearest of the slaves have wrong data. So that's inconsistent. Okay, so availability is not always available. Consistency is not always consistent. So in the end, and the network partitions, of course, they happen, but they're very, very rare. So if you exclude for a moment the case of going to the mountains, okay, if you are in, I would say in the connected environments through cables. Okay, so we remove Wi-Fi and all the mobile connections and all the stuff. You are connected to the Ethernet cable. Okay, the probability of having a failure in a network is very, very low. Okay, I don't have any memory of having a failure in a network cable. I have a failures Wi-Fi sometimes on my mobile through the tunnels in the mountains and everywhere. But to have a failure in the cables must be there is maintenance intervention, but you can prepare for that, or there is actually a failure in the router. Yeah, might happen, but very rare. So in the end, you have availability, not always, even without the CAP theorem. Okay, consistency, not so consistent in real time. Okay, you have some delay, eventually consistent. Network partition, very, very low in probability. So what happens in the end is that given that the network partition is low in probability, but very low in probability, so it always never happen. Also because over the network here, I've drawn this line and nobody told me anything, but actually what might happen more probably is something like this. Okay, so you cut one of the connections, not everything in the Atlantic Ocean is cut down. Okay, so in the network, in the internet nowadays, luckily, we have many different routes to reach a destination. Okay, and so this provides also redundancy from a network point of view. And so the network partition is very rare because you need to have a network congestion or a cut of a wire or very special maintenance or something like this. Okay, it's a very bad event, and it's typically transient. Okay, so in the end, given all of these, what happens? It's here. The spoiler is that the CAP theorem is kind of true, but never applied, because if you have no network partition, because it's very rare, and the availability and the consistency are already capped at 99.99, in the end, your system behaves as if it were CA and P compliant. Because you never experience the P, the consistency is so fast that you don't experience the inconsistency result, and the availability is capped by the SLA, by other factors, not by the CAP theorem. Okay, so in the end, your distributed database behaves like if it were CA and P compliant at the same time. It seems to be. Okay, thanks to the transient and to the smoothed features, which are not, I have availability, I don't have consistency. No, you are available most of the time, 99.99%, and you are consistent in 100 milliseconds. So you're not neither available nor consistent, actually. But in the end, the behavior from your application point of view is like if you were both. Okay, and that's acceptable. Okay, so that's the idea. Yeah, we must have a break now because it's 1 hour and a half over. Thank you. Okay, let's have a 10 minutes break. Thank you. I know it's Okay. So let's check that everybody in the Zoom meeting can hear me. Okay, yeah, it's working also in the Zoom meeting. Great. So, yeah. To do what? I think so, but I don't. Do we have the control? There must be some kind of control here. Yeah. Okay. Okay. So, I think it stops automatically. Just check that. Yeah. Okay. So, if finally we can check the properties called acid, and then we see the counterpart in NoSQL. Okay. So the acid properties I mentioned quite a lot of times are the following. Okay. This arises from relational databases. So some of you should know them. Okay. Let's have a recap. Atomicity, which means that this relates to a transaction in a database. So a transaction in a database being distributed or non-distributed, we don't care, but we want as a user of the database. So here we are, okay? We are a user in the database. So this user is using the database. This user is using the database, okay? Two users are using the database. They would like to see what? They would like to see that their transaction, their operation, their update or insert is executed with an atomic approach, which means that either it's done all, so it's fully completed, or it's done nothing. Okay, so you see, if you move some money from my bank account to your bank account, we cannot accept that half the money is transferred. Either it's done all or nothing. Okay, cannot be partial. Okay, consistency means that's different from the consistency of the CAP theorem. Okay, unfortunately, they use the same English word both in the CAP theorem, C stands for consistency, and in ACID, C stands for consistency. But in the CAP theorem, we say it's the same data in all the points of the database. Okay, so we are here, all the users around the distributed database, they see the same information, the same data. So all the queries turn the same data. Instead, in the ACID properties, we mean that the data respect the rules, like in a primary key constraint, referential integrity, so foreign key constraint, and all the stuff. Okay, that's the consistency. Then isolation is the following. In a database, you have typically thousands of transactions per second in parallel. But the database must handle them as if they were alone. Okay? So each transaction must be executed as if that is the only transaction being executed, even if in reality it's not like that. They go in parallel. Okay? And finally, durability means that when I confirm I've done the money transfer from my bank account to your bank account, it's done forever. Okay? It's not, okay, I tried, I don't know, it might be. No, it's done. Written to disk forever. Okay? That's it, durability. In the NoSQL, they copied the joke on ACID by trying to fit the base, of course, by contrast, with some features. And the features they've chosen for the base acronym are basically available. This tells you that the priority of NoSQL is to be available, which means I generally allow the customers to operate under any circumstances. No matter the network partition, no matter the consistency, I try to be always available. Okay? It's basically available because, of course, it's a priority. It's not a rule. Okay? Sorry. Soft state eventually consistent is the second part I stressed before. So soft state eventually consistent has to do with the fact of if you know the DNS system, you know what I mean. Okay, it's a behaved like a NoSQL, but the DNS was invented much before the NoSQL. Okay, the idea is the following: I update my data, and then softly, eventually, my updates propagate to all the nodes, so that after a while, all the nodes are consistent. Okay, that's the idea. And if this delay is small enough, the probability of conflicts or problems is very low. Okay, that's the idea. So you have a comparison here, which is the things I've just told you. Let's just take an example. This is very brief example of how CouchDB, which is a pure NoSQL, handles the conflict detection and resolution. Okay, the idea is the following: I have two customers, like X and Y in a previous example. They are booking the same room at the same time, and since we are using NoSQL, the conflict happens. Okay, no, the NoSQL is not checking with all the nodes if nobody has booked the same room at the same time and so on. It just allows booking, basically available. Book, book, book. Income, money, okay? Then I know I'm overselling. I must automatically detect the conflict, which means there is a problem. Okay, I raise the hand, there is a problem. I've booked the same room to two different people, okay, in the same period, okay? There is a problem. So detecting the conflict is important, because if you don't know about the conflict, it's much worse. Okay, so the two people will arrive in the hotel and they claim, I have the keys, I want the keys, I have the booking, and that's a nasty problem. Okay, I need to detect it early so that I can manage that by gifting or whatever. Okay, so detection is paramount. And then the other option of CouchDB is to provide you with a solution in which I eventually converge to the same consistent state across all the nodes. Okay, it's like if we could organize a pizza without distributing phone calls or any kind of agreements, okay? Without organizing a meeting for that. Everybody tries its best, and in the end, with this protocol, we end up having the same result, okay? Which is not the best result, okay? It's the same result, which means you converge for consistency. But then if I assign the room to customer A or customer B, it's not my choice as database, okay? I have to converge to that to guarantee the consistency eventually, so after a while. But then it's the post-sales assistant job to decide which customer goes where, okay? So that's it. So the example is very simple. You want to book a hotel room, so you have the two nodes. So you have customer A and customer B. They operate on different nodes here. So if you want to look at the history of the documents, I would say on the node on the left, that's the timing which goes on. And this is the timing which goes on node B, okay? So at some point on the node A, someone books that room to the customer A for that period, okay? And at the same time, this happens on node B. So when A propagates the change to B, saying, hey, eventually consistent. So when I have an update, I propagate the update to the other nodes, okay, so that they catch up at some point. I propagate the change, B detects the problem because B has changed the document. It's a NoSQL document based, and receives a new document after the change. Okay, and so you say, I've changed the document. I should issue an update to the others. Okay, instead, they are telling me to update my document. This is a conflict. This is done with the revision number. Okay, in CouchDB, they use an attribute called _rev, which is a short version of revision number. Every time the database updates document, it automatically increases the revision count, like an auto increment. So you know that if you receive an update with the same revision number or a higher revision number than yours, you have a conflict, okay? Besides that, there is another trick. CouchDB creates a hash of the content of the document. Okay, the hash function, I think you know the hash function. It's a non-invertible function which generates a very short digest, okay, a few bytes of digest, which is kind of random, okay? So it's kind of a signature of the document. If you just change a bit in the document, the hash is totally different, okay? And so this is a kind of a signature of the document. So two documents with the same content, they have the same hash function. With a small change in the content, totally different hash functions, okay? So you generate this string, basically it's a string, the hash function, the hash value, and it's appended to the revision number. So that if you receive two documents with the same revision number, but different hashes, you know that they're different in content. And this is the trick. How can CouchDB decide which is the winning one? Just by chance, which is higher in lexicographical order. So you take this string, which is the hash function, and you say the higher wins. In this way, everybody in the nodes, because you see two nodes only, but imagine you have thousands of nodes like these. They all received update from A. Some of them might have already updated the booking of the room with new revision number, with new hash value. And they receive the conflict, detect the conflict, and they don't need to call the other node, say, let's agree on which is winning. No, the algorithm is local. I do the sorting of the hash, and the highest wins. So if I win, I propagate my change, and it will win against all the others. If I've lost, I just accept the new update and I detect the conflict, I raise the hand, there is a conflict, but I save as the latest winning version, the highest with the hash value. And so every node will, at the end of this process, will contain the booking of the room associated to one customer, which is the same for all of them. Okay, so that's the goal of the database, not to decide which customer in sense of human values. So the first who booked, or no, you choose the criteria. Okay, just to become consistent, so that from a certain moment on, everybody asking to the database whose booking is this, the answer will be the same from all the nodes, which is the property we like. It's called consistency in CAP. Okay, that's the idea. And so this is what happens with the ref value and ASCII order of the hashing. Okay, so that's a very tiny example to let you understand what Werner Vogel says when you need to have an algorithm which converge without asking to the whole people, hey, what do we need to do with this customer? Okay, so everybody knows what to do. The highest wins. Yeah, it's random. Okay, no problem. But then the escalation is application level management. Okay, so that's the idea. Please. Because timestamp is a problem. So the question is, how can we use the timestamp? Timestamp can derive, okay, first. Second, the problem with the timestamp basically is an alternative to the hash function. But the hash function is kind of universal. You can replace the hash function whenever you want. You take the document, you compute the hash function, you get the value. Okay. The timestamp is assigned by the node itself. So you must keep the node synchronized with the others. You might have some kind of drift. You might have not so precise clocks. Okay. You might have many different issues with the timestamp. It's acceptable. You might decide, I insert a timestamp, the local timestamp, and then the highest in timestamp wins, or the lowest, which is the first, wins. No, time is universal as an idea, but the time reference. So if I ask you the time, okay, we all have digital clocks and internet connected clocks. But if you look at, I would say, the milliseconds, they change. There is a drift. Okay, there is a drift. If you look at the clocks before internet, There were some kind of minutes in difference. Okay, so nowadays you can reach, I don't know, some seconds of alignment. But then, besides that, if you look at the milliseconds, you're not sure if that is the right millisecond or not. Okay, so it's an option. I mean, it's an option similar to the hash function to have a sorting based on the timestamp. Then it's your job to keep the timestamp aligned. Okay, that's the idea for sure. Okay, fine. No, it's not a computational problem because computing timestamp is easy. You get the timestamp very easily. Every computer has a timestamp inside. It's just the date and time, the number of seconds since the epoch. So if you know the current date time, you know the timestamp. Okay, it's not a problem. Timestamp is a complexity. Is a problem of having a method which is local in this decision. So you are a node. You don't need to ask the others. Let's give you a very trivial example. We need to organize the pizza of the class. Everybody says a date, okay? And we decide the protocol is everybody takes the max. So I say a date and I launch a date to all the others. You say a date and we do all the same. So I receive all the dates of the others. I do the max function. We take the latest one, so the farthest one. In one row, one run, we all know the pizza will be on the latest values everybody said. And we didn't organize a meeting. We didn't exchange anything apart from the date. That's the idea. Then it will not be the ideal date probably. But the problem is not the ideal customer. The problem is being consistent. So if someone asks us, when is the pizza of the class? We all know it's the max. So we answer the same answer. Okay, we reply with the same answer. Okay, please. Yeah, okay. I know this, I didn't mention this. The revision number is local to the document. Okay, but thank you. Thank you for pointing it out because now it's clear. Yeah, the revision number is written in the document of the booking. We say in the document of the room booking, I would say. So in the room, you have, every time someone books the room for that period, that case, you increase the revision number. Okay, this is a very tiny example to give you the idea. We would have a full lecture on these topics, but we don't have time. So just to tell you, there is a mechanism in case you have the pointer to the stuff and you can study that better. But that's the idea. Okay, thank you. Great. Okay, so please. Yeah. The question is, do we need the revision number for every document in database? Actually, in CouchDB, it's for free. So CouchDB automatically provides you with a revision number management, and the revision number is managed by CouchDB itself in the background. So every time you create a document, it automatically has a revision number, and you take the benefit of the automatically increase or the auto increment and the hash function and all the stuff. So it's done, I would say, in the background. It's service, like the primary key in relational databases. Okay, and also CouchDB has keeps track of the versioning of the document. So in CouchDB, you can ask for that document with that revision number in the past. So it's kind of a Git system. Okay, and so then of course sometimes you clean that because that occupies space. You have the trade-off, but it's very useful because you make a mistake, you can always revert as long as you don't purge. It's called purge, the deleting of the old versions. So when you purge, all the old versions are revisions are removed, and you only keep the latest. But if you don't purge, you have all the history of the document with all the changes, and that's useful. Okay, great. You see, this is just not a NoSQL. We don't have time to talk about, but that will be very interesting to investigate. So NoSQLs are very broad. So everyone has its own pros, cons, and very broad topic. Great. So now we focus instead to look at all this stuff on MongoDB. Sorry, MongoDB. Okay. So it's this one. Okay. Because tomorrow you will practice on these. Okay. So how does the replication works in MongoDB? In MongoDB, we have some key concepts, which are the following. First, we divide the nodes in our distributed database in 3 cases. Okay, you can have nodes of 3 types: a primary node, a secondary node, and an arbiter. Okay, so the primary node is only one. In the past, it was called master node. Now they call it primary. Okay, so it's similar to the master node of the previous slides. It's only one. Okay, then you have secondary nodes, which are the slaves. Okay, and so they catch up the copies of the data from the master, from the primary. Okay, and then you have the arbiter, which is optional, which is not present in our general framework. The arbiter purpose is just to elect a new primary. So if the primary dies, if the master dies, then from the slaves, from the secondary nodes, you must select a new primary. In case there is a tie, so you have 5 nodes, the primary dies, you have 4 secondaries, and the 4 secondaries during the election, they vote 2, they vote for a node, and 2, they vote for another one. You have a tie, you cannot do anything. So the arbiter is used to avoid wasting the resources of a new secondary, because a new secondary means a new slave with all the copies of the data. So a slave is a heavy operation because you have a copy of the whole data, okay? And it's expensive. Instead, the arbiter just votes for the election, nothing else, okay? It has also some implications on the network partition, because you can put the arbiter when you want the primary to be elected, but that's advanced topics. Just remember you have these 3 types, okay? Then in case you need, of course, you need to study much more than what I can teach you in these few minutes, okay? But just to give you the idea, the core concepts. So primary nodes is like the master, receives all the write operations. Each write operation can have a write concern. A write concern is what we called before the synchronous or asynchronous replication, okay? So the write concern tells MongoDB, the primary MongoDB, how many slaves, how many secondaries to wait for. The quorum, only one, at least one, none, all of them. Okay, so you can trade off the reliability and the speed. Okay, so if you have a low requirements in speed, you can increase the availability. If you want high speed, of course, you need to decrease reliability. If you have very far away nodes, far away secondary nodes, it's better to reduce to avoid using all. Okay, that's the right concern. And so it waits for those amount of secondary nodes to acknowledge the replication of the data of the instruction, basically insert, update, or delete. Okay. The secondary nodes are the slaves, so they replicate the primary is oplog. Oplog is a term for MongoDB, which is called operation log. Every database has a log of the actions executed on the database. Okay, so how can you replicate what happens? You read the log and you execute the same operations. Okay, that's it. So it's called oplog, operation log. If the primary is unavailable, and now, how can you know if it is unavailable or if you have been disconnected from the network? And how long do you wait for being unavailable? Because if the primary doesn't reply in 1 millisecond, 10 millisecond, 100 millisecond, how long do you wait? Okay, so that's an open issue. You can, of course, configure that value. Okay, there are some defaults, but the point is, when you detect based on your thresholds that the primary is not available anymore, then you start the election process. okay, to elect a new primary, okay? Some slaves can also be, or secondaries can also be non-voting, okay? Why there is such a complexity in the election? First, because when the election happens, it is because there has been a failure, and so it is something which must be handled with care. Second, you don't want to elect the Australian secondary to become the primary. Otherwise, all the rights go to Australia and then go back to Europe for the replication, and the acknowledge goes back to Australia, and from Australia we reply our customers in Europe. Okay, so that's to be avoided. So you configure the replica set of MongoDB in such a way that arbiter and the secondary will elect another secondary node which is suitable to become a primary. Okay, and so you can set some weights. There are some specific configurations for that. Okay, you can deep dive when you work with that. It's easy, but just to give you the sense of these. Okay, so the election of the new primary must select from the secondaries node a node which is suitable. Okay, that's the idea. Finally, arbiters, they do not hold data. They're empty, just processes for voting. Okay, and for voting towards the right primary. Okay. Also, because when you disconnect from the primary, it might happen that you actually had, these nodes here. Okay, these are the nodes. Okay, there is a network partition like this. Okay, these two, they talk to each other, so they might think, we are the only two. I'm the primary, you are the secondary. Let's work. That doesn't work. Okay, because if they continue working, they diverge. They keep booking rooms. Okay, and they diverge with respect to the others. Instead, here you have a minimum amount of nodes that you must be aware they're alive so that you know you're on the right side of the partition. Okay, and so for this reason, you put the arbiters on that side so that the right side continues to operate. Okay, in case you want that kind of behavior. Okay, that maintains a quorum. Okay, in a replica set. That's the idea. So that's the idea of the architecture of the MongoDB replica sets. You have the client application, which writes and reads. Typically, that works towards the primary by default. And then the secondary just replicates the data. If you have an arbiter, you have the replication going only towards the secondary, and the arbiter just keeps it heartbeat. Heartbeat means exchanging messages from time to time to keep it alive. Say, I'm alive, yes, that's okay. So you can detect if the other node is not alive or if there is a network partition. Okay. Of course, you can direct the reads to the secondary. Okay, that's possible. That's the purpose of all this stuff. Okay. That's an example of the different write concerns. So write at least once, write with the majority of them. Okay. So you write always to the primary. That's written to the primary. Okay. It applies locally and then waits for the other to apply. So if the write is only at least one, I send actually, I would say it sends the replication in parallel to all of the nodes. Okay, it's not actually later like this. You send it to all of them, and then the first which replies generates the response back. Okay, so at first reply, you generate the response here. Okay, yeah. So with W1, which is write concern at least one node, as soon as it is locally applies write. Yeah, actually, write concern one, yeah, that's correct, means one including the primary. So write concern one means that at least one node, including the primary, must have written that. And so generally it's the primary itself because it's the fastest. Okay, so you must set at least two nodes in the replica set to get at least one slave as a copy. Okay. That's the automatic failover. You see the default period is 10 seconds. So you have these heartbeat exchanges, keep alive messages. If for 10 seconds we cannot get in touch, then I consider the other node to be offline or myself to be offline. How do I know? I try with the other nodes in the replica set. If I cannot speak to anybody else, I'm under the quorum, no election. Means I'm alone or I'm on the minority side of the network partition. Okay. Instead, if I can still contact the other nodes, we reach the quorum, so we have quite a few, we have more than the half, okay? We can elect a new primary and we keep operating ourselves. And then when the other partition will get up, it will synchronize with us and will catch up the changes and then become operative after a while of catching up. Okay, so that's the idea. The time for the election of the new primary typically is 12 seconds. You see, it's kind of a long time in our world of real-time things. So if you have a real-time service like playing a game for 12 seconds, you are stopped. You know, it's not very nice if you're paying, okay? But anyway, nice thing is automatic. So even if it's, you know, in Christmas, you are on holiday, it works, okay? It's self-healing, okay? It self-elects a new primary. You must have set correctly the weights, okay, such that a new primary which is suitable is selected. That's cool, okay? Okay. Now, this is a table which shows you what? Given a number of members of the replica set. Okay, so I put together one primary and a certain number of secondaries, and also possibly arbiters, okay? Whose number is this one, okay? So 3 means 1 primary and 2 secondary. 4 means 1 primary and 3 secondary. Then when you have a lot of nodes, you can also have arbiters. The problem with arbiters is that they have no data. So if you have 1 primary, 1 secondary, and all arbiters, you can survive only to 1 failure, because you kill the primary and you still have the secondary. That's it. Because if you kill the primary and the secondary, the arbiters have no data, so they are kind of useless. Okay. So imagine you have primaries and secondaries here as number of members. So 1 primary and all the others are secondaries. The majority required to elect a new primary is, of course, half plus 1. Okay, so out of 3 is 2, because it will be 1.5 plus the higher integer. Okay, and so that's the numbers you get from the number of nodes to elect new primary. But the interesting stuff is the fault tolerance. Fault tolerance means how many nodes can I kill or can I have a problem without disrupting the system. So after that number of failures, that number of nodes have been disconnected, destroyed, unavailable, the whole system is still available. Okay, so that's the degree of resilience to the failure. And you see that if you increase by 1, actually, you don't get any advantage in terms of number of tolerance. Okay, and again, here, if you jump, you don't get the advantage there. Okay, so one exercise I gave to some exams ago, you can find it on the website, was to compute that for the next number, for instance, okay, to see if you got Y, okay, because it's very easy. You build the primary, okay, you build the secondaries, okay, and then you try to kill them. You say, if I kill 2, the majority required is 3, I cannot survive. Okay, that's the problem, because to elect the new primary, you need at least half plus 1 be available. Okay, so that's the majority required. Okay, so you see here, 6 minus 2 generates 4. If you have 6 nodes and you kill 2, you still have 4, and 4 is the number you need to elect a new primary. So it works. It survives. Okay. If you have 5 minus 2, it's 3. Okay. So if you have 5 nodes, you kill 2, you still have the 3 required for electing a new primary. Okay. So that's the idea. Yeah, the default operations, so there are 2 implications here. First, the default is asynchronous replication, okay? That's a default behavior and generates, of course, a lag, an inconsistency, okay? And the second point is that you can also use multi-document transactions, which means that you can, start a transaction which affects different documents. So you must change different documents. And then you stop when you end changing all the documents and you commit them all. Okay. And this, of course, is expensive. Okay. Because you cannot stop in the middle. If you stop in the middle, everything must be reverted back. Okay. Okay, that's the reading from the secondary. You see, you can read from the secondary like this, and while the writing goes always to the primary. That's the default master-slave replication here. Here we have an example in the next slide with some commands. I just comment the key points, then you will do this practice in the lab practice. I don't know if Simone will make you using Docker images or native MongoDB, but you can do in both ways. Okay, I will show you the native version probably. He's showing you the Docker version, I think. So here, the instructions for deploying a 3-member replica set, because that is the minimum. It's the minimum, because if you have 2 members, when one dies, you don't know if it's disconnected from the other, so which is alive. Okay, so I have 2 nodes here. Okay, I have 2 nodes. They disconnect. They can't talk to each other. Okay, which is winning? Nobody knows. Okay, because we cannot decide. Okay, so that's impossible as 2-member replica set. A 3-member is different, because if you have a 3-member, at least 2 of them, 2 of them can talk to each other. So they say, we are the ones who are alive. It's the other who has been disconnected. So we can elect a new primary and keep working. Okay, that's the idea. So 3-member is the best. Then odd number is always again a new best practice, because when there is a failure, you have an even number for the election. Okay. Yeah, another very common situation is separation between members on separate machines. That's just best practice, not for MongoDB, but for any distributed database for resiliency to disaster recovery. Okay. In our case, we generate the following. I'll show you in a minute. We generate 3 instances for the purpose of the lab practice and for you to play on the same notebook. You just launch MongoDB on different port numbers, okay? And then you can connect to different port numbers. You configure the replica set so that each of them knows to belong to the same replica set. And then you try to, kill one of them and see if the primary changes. Change the weight of the primary and see if you can make the one you want to be elected, and so on. Okay. Yeah, here you have some suggestions for the practical aspect. Here we have the ideal. So you have 3 members. Imagine these are the 3 replica set instances, MongoDB 0, 1, and 2. You launch MongoDB by saying you launch each of them. Okay, so the first, the second, and the third, saying you belong to a replica set whose name is this one, RS name for this case, replica set name, but you choose the name, okay? And then you bind it to a given IP or localhost or host name or address. We don't care actually about that. Here, you launch then each of them. Okay, so these are 3 instances, 3 different processes of MongoDB. By chance, they've been launched on the same machine. We don't care. They could be on different machines. Like here, they were on MongoDB 0, MongoDB 1, MongoDB 2. I'm just launching them on localhost now here. They belong to the same replica set. Okay, they belong to the same replica set. They are bound to different ports. Okay, port numbers, of course. That's an implication of the operating system. And then you pass different paths. Okay, so you build a directory for the replica set name 0, then a directory for the replica set name 1, okay? So each one is independent, different port, listening on different ports, and storing data on different folder on the hard disk, okay? And then you connect to one of them, you open the shell, okay? And you issue the replica set configuration, given the name and the list of the members, saying the host name and port to connect to. So if it is the same host name, like localhost, they're on the localhost. If you provide 3 different names of the 3 different machines, They must only be reachable, okay? But it can be everywhere, in Australia or whenever you want, okay? Then, of course, you need to harden that, put SSL, a password, and everything, because I'm skipping that, okay? But anyway, in this case, they are on the same host name, localhost, different ports, and they automatically configure themselves to work together, okay? This seems to be kind of trivial or given for granted. Nowadays, it's given for granted. You're right. When I started studying this stuff 15 years ago, I spent 6 months configuring Tungsten. Tungsten was an extension of MySQL for doing this. Okay, and after 6 months, it worked fine for the first few minutes, and then it died. Okay, so this just to tell you the maturity of the stuff. Why? Because MySQL was born to do other stuff, not this one. MongoDB did that from version 2. Okay, since the beginning, this was out of the box and it worked fine. Okay, so I was astonished when I tried that and said, well, I spent 6 months, it didn't work, this is 1 minute. Okay, so how long did it take to do that? Yeah, 1 through 3 commands. Yeah, creating 3 folders, launching 3 commands, and giving 1 operation configuration here. So in 4 steps, 4 commands, just cut and paste, you have a fully functional replica set, distributed database, yeah, on your own machine. But you just change the binding here. You choose 4 host names, 3 host names, 3 servers you have access to, and it's working. Okay, and so then that was quite interesting for me. Okay, then if you connect to the primary, you can issue some command with replica set rs dot, for instance, add. You can add the new nodes. Okay, so install MongoDB on the new node, the 4th one. Okay, you tell that instance you will belong to that replica set, and you use the same name of replica set. Then you connect to the primary. You say, hey, you have a new secondary. Please let it join. It joins. It receives all the data, creates a copy. When it's ready, starts working. Okay, and then you have a lot of, I would say, configuration patterns. We cannot see them all. You can have, yeah, you can get the current configuration. You can change the priority. You can change the value of the voting. Okay, so the priority is the probability of getting the primary when the primary dies during an action. The number of votes is how weight has your vote. So how many votes you cast, basically, as a node. Okay, and this allows you in configuring a suitable secondary to become primary in the right data center, near to the place where you need it, with the right hardware. Okay, because you might have some slaves, some secondary, which you don't use for any other purpose than just having a backup. Okay, so they are very low quality machines, and that's okay. You might have other secondaries which are in hot standby. So as soon as the primary fails, they are ready to become primaries. Okay, because very, very good machines. Okay, and you can also remove members. So this is for adding a member. Okay, adding a new member with these. Okay, so you create, of course, the instance. When it's running, you go to the primary, say, hey, you have a new member. Let's do the onboarding. Or you can remove one of the members. Okay, so you go to the primary, you say, please remove that member. It issues the command and releases that. Okay, you can then verify replica set, see the status. You can play with it in the lab practice. I've indicated here some examples. Okay, so members, you have a list of members here. You see a list of members. So ID, the host. Is it an arbiter only? False. So it's not an arbiter only. It's a secondary. Then hidden priority. You see priority to become a primary, number of votes, and all the stuff. Okay, so you have a lot of parameters for fine tuning, but that's very specific for the product. Okay, and then you have some other settings here. Okay, just to show you that. Okay, so that's something you will play with in the lab practice tomorrow. Okay, then tomorrow you have the lab practice on 3 teams. We have seen that now there are not so many students joining the lab practice to justify 3 teams. So from the next week, I propose to have 2 teams only. for the lab practice. Okay, so I will publish the timing. We'll probably remove the first, which is the least. So and we are seeing the last team. So from 2:30 to 4 is the most popular. Okay, so we will keep that, even if in the origin there was no timing on that. So we added that. It's a new one. Okay, but we keep that because we have seen that most of you joined that one. Then to avoid having a hole in the middle, we will pack the two teams from 1 p.m. to 4 p.m. Okay, so we will cancel the first one in the morning. Okay, so tomorrow 3 teams. Next week this change I will put an announcement in the. Then on Thursday you have Diego Monti. So on Thursday there is a first lecture of data visualization. Okay, so that's all. See you next week with me. Okay, thank you very much.